To the first carbon atom bromine which is attached, there is no branching at all, hence their boiling point which is very high. Silver ethanoate. Why it is silver ethanoate? We have replaced the H by using silver, so it is silver ethanoate. Suppose if my reagent is NaOR dash, so nucleophile will be R dash O minus and the product will be ether. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called Haloalkanes and Haloarenes. Under that, we have discussed about the nomenclature of haloalkanes and haloarenes, and also we have understood that the nature of carbon and halogen bonds in the haloalkanes and haloarenes, and also we have deeply discussed with the method of preparation. Today, we'll step up to understand the physical and chemical properties of haloalkanes. Okay, so first I'll go with the physical property. In that, first we will understand the physical state of the haloalkanes. Okay, so physical state and smell, it says that the haloalkanes are usually colorless, odorless, and it is a colorless and it is a sweet smelling liquids, and the lower member if you consider like methyl chloride, that is, so methyl chloride, ethyl bromide and ethyl chloride are colorless gases, while the members which are having high molecular masses are become solid, which indicates that the physical state of this lower member of haloalkanes are usually colorless. As the number of carbon atoms which has been increased in the chain, it becomes very strong, hence it behaves like a solids. Okay. Coming into the density, we know that density is nothing but a mass by volume, right? So, the bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water, and the density will be increases with increasing in number of carbon atom and halogen atom and atomic mass of the halogen atom. We know that the haloalkanes will be generally represented as Rx, right? So, Rx. We know that this R will be stands for alkyl group and this X stands for bromo, iodo, chloro or fluoro, and these are the halogen atom. As the number of carbon atom which increases, automatically density which is also increased. As the halogen atom which is also get increased, density which is also get increases. Coming into their boiling point and their melting point, greater the molecular masses, stronger will be the van der Waals force of attraction. Hence, the greater will be the melting point and boiling point. So, what does it state? As the number of carbon atoms is increased, obviously there will be a more van der Waals force of attractions, and as a result of this, their melting point and boiling point both will get increases. So, in that first case, for a same alkyl or with a aryl group, suppose if the same alkyl or aryl groups are there in the haloalkanes, the boiling point will be decreases and it will be goes in this order, whereas the alkyl group with the fluorine has got very least boiling point. Okay, so you can see that the alkyl iodide will have a more boiling point or highest boiling point because of the increasing their nature of the same or different alkyl group. For the same halogen, the boiling point will be decreases as the size of the alkyl groups are decreased. Okay, so for the same halogen, if it is there on the carbon chain, the boiling point will be decreases as the size of the alkyl groups which is also get decreased. So here we have an example. You can see that this is CH3, CH2 and X. Again, one of the CH2 if you remove, it becomes CH3, CH2X, and one more CH2 if you remove, so it becomes what? CH3X. So here X stands for chloro, bromo, and iodo, chloro, bromo, iodo, as well as with the fluoro. So here you can see that as the number of carbon atoms which is going to be reduced, their halogen atom which is also get reduced, right? So this indicates that for the same halogen, the boiling point will be decreased with number of alkyl group which is also get decreased, okay? For the isomeric alkyl halides, boiling point will be decreases as the branching which is increases. So you can take this by looking at this example. This is CH3, CH2, CH2 and Br. You can see that this is a carbon chain where it does not have any branching as with compared with the two example. And the name of this compound is, so it is 1-bromo-butane, and to the first carbon atom bromine which is attached, there is no branching at all, hence their boiling point which is very high. So compared to the second example, this is 2-bromo-butane. Again you can see that to the second carbon atom there is a somewhat branching which is occurred due to the substrate group, hence it is the boiling point will be decreased as with compared with the first example. Suppose if the bromine group which has been attached to the second carbon atom where it has too many branching, you can see is that as the branching which is increases, their boiling point which is also get decreases. Okay, so this is how we can understand the boiling point of this haloalkanes and haloalkenes by looking at with the example. Among, if you see that physical state, okay, among the dichlorobenzene, so this is a 1, 2, 3, 4, 5, 6. Again 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is 1, 2 dichlorobenzene. It is 1, 3 dichlorobenzene. It is 1, 4 dichlorobenzene, and this is ortho and this is meta, ortho position. So here it is present at the meta side and this is will be present at the para. Okay. So among the dichlorobenzene, the para form, if you see that, okay, para isomer are being symmetrical and packed very closely in the crystal lattice, hence it has higher melting point than that of the meta and ortho. If you see that boiling point and the melting point of these two compounds, if you consider the ortho and the meta, so ortho will have 453 whereas the meta will have a 446, whereas a para position of the dichlorobenzene, it has 448. This indicates that their boiling point will be decreased. If you see that melting point, the para position of the chloro in this dichlorobenzene will be more closely packed, hence their melting point which is also very high as that of the meta as with the ortho. So why it is very high? Because of the closely packed structure of the crystal lattice which makes this para dichlorobenzene as with a higher melting point. You can see that melting point will be 323, for meta it is 249 and for ortho it is 256. Okay. Next we have solidity. So we'll see whether haloalkanes or haloarenes, whether it will be soluble in water or not. Although haloalkanes are polar in nature. Why it is polar? We have already understood that it has a chain of carbon and halogen bond. We know that it is since the carbon which is donating its bond towards the halogen will get a partial negative charge, whereas a carbon atom which gets a partial positive charge, and the nature of this bond will be polar, right? Yes. Although haloalkanes are polar in nature, yet they are slightly soluble in water. In order for the haloalkanes to dissolve in water, energy is required to overcome the attractions between haloalkane molecules and break the hydrogen bond between the water molecule. However, the haloalkanes are not able to form a hydrogen bond with the water. Therefore, less energy will be released when attractions are set in between haloalkanes with a water molecule. As a result of this, the haloalkanes will be in water will be very low. Their solubility in water will be very low. So we know that the haloalkanes, in the sense it has carbon and halogen bond. Since it consists of halogen, it is insoluble in water, or we can say that it is slightly soluble in water. If you make a setup by dissolving or by making the attractions between the hydrogen bond of the water with this haloalkanes, so this haloalkanes will become very less soluble as that of with the original solution with the water. Next, we have chemical property. In this, we are going to understand how does this haloalkanes which shows a different chemical property. In that, mainly we are studying about nucleophilic substitution reaction, elimination reaction, and reactions with the metals. Okay, so the reaction of haloalkanes may be divided into three types. They are nucleophilic substitution reaction and elimination reaction and reactions with the metal. First, I will go with the nucleophilic substitution reaction. So, before going to understand this, we need to understand what is a nucleophile first. Okay. So, nucleophile, which is nothing but negatively charged species, which always attracted towards the positive center, that is towards the nucleus, you can say. Okay. So, what is a nucleophile? Nucleophiles are negatively charged species which is always attracted towards a positive center known as nucleus. Okay. So, this nucleophilic substitution reaction, how does it happen? So, we will understand first. This is a type of reaction where a nucleophile attacks a partial positively charged carbon atom in carbon-halogen bond. So, we know that in the haloalkanes, the carbon and halogen, they have polar bond. This carbon is donating its electron towards a halogen. Hence, a halogen will get the partial negative charge, whereas a carbon will get the partial positive charge. Since the carbon atom is having partial positive charge, our nucleophile, okay, since it is having the negative charge, it will be attracted towards a positively charged center known as carbon. Thereby, it forms what? Nucleophilic substitution reaction. It forms what? Nucleophilic substitution reaction. So, it's what? Nucleophilic substitution reaction, where the halogens will be get separated out. A new bond of carbon with the nucleophile which has been formed and leaving a halogen atom separated out. This kind of reactions are known as what? Nucleophilic substitution reaction. Remember, nucleophiles are the species which always attracted towards a positive center. Since we are talking about the nucleophilic substitution reaction, if you consider the general reactions for representing an haloalkane, we know that haloalkanes will be generally represented as CX, where the carbon which is having partial positive charge, whereas the halogen which is having partial negative charge. Our nucleophile character is to go and attack for the positively charged center in the nucleus, right? So, especially it will be goes and attacks to the positively charged center known as carbon atom. Thereby, it forms a new bond between the carbon and nucleus. This kind of reactions are known as what? Nucleophilic substitution reaction. Next, we have reactions with aqueous KOH or with aqueous NaOH. Okay. When alkyl halide is treated with aqueous KOH, which is also known as what? Potash, or aqueous NaOH, corresponding alcohols has been formed. So, here again R stands for CH3 or C2H5, anything. Okay. So again, X will be stand for chloro, bromo, iodo, etc. So when it has been treated with alcoholic KOH, that is potash, what does it happens? Again, the K, that is potassium, combines with the halogen to form a KH, whereas this OH goes and attacks to this R group, that is the alkyl group, thereby forms an alcohol. We'll take one example. Okay. So I'll take the R as CH3, X as a Cl, or you can take Br also, plus KOH, which is aqueous. Okay. So what does it gives? This K combines with the Br to give a KBr, and this remaining alcohol will be formed, right? So it is methyl alcohol or methanol, you can see. Okay. We'll go with the one more reactions. C2H5 Cl, that is, okay, NaBr, NaOH I'll take, aqueous. So what does it forms? Remember, the sodium combines with the chlorine to form a sodium chloride, and C2H5OH will be formed, and it is an ethyl alcohol. Ethanol, you can say. Ethyl alcohol or ethanol. This is how, by considering aqueous KOH or with the aqueous NaOH, by writing with the aqueous KOH, remember we have to write what? KBr. With aqueous NaOH, you have to write NaCl. Okay. So this is how, just by exchanging with the Cl as exchanging with the halogen or with the R group, we can rewrite the reaction by taking the plenty of examples. With alcohol KCl, let's see how does it forms a reaction. Okay. When alkyl halides has been treated with alcoholic potassium cyanide, alkyl nitriles will be formed. Alkyl nitrile, which is also known as what? Cyanoalkane. So we'll see with the general reaction. Okay. So Rx, this is a general representation of what? Haloalkane, which has been treated with KCl, that is potassium cyanide, which is upon heating. Again, this R combines with the Cn to form a RCn, and K combines with the X to form a KX. So here, this again, R will be replaced with a CH3 or C2H5, and X will be replaced with chloro, bromo. Okay. So you can take the example of CH3Br and KCl, which is upon heating, which gives rise to the CH3CN and KBr. Similarly, you can take C2H5Cl and KCl upon heating, which gives rise to the C2H5Cn with the KCl. So it is propane nitride and it is ethane nitride. You can take one more example, CH3, CH2, CH2Cl. Okay, it is propyl chloride. Okay, in presence of KCN, alcoholic, upon heating, what does it forms? K combines with the Cl to form a KCl, potassium chloride, and this forms CH3, CH2, CH2Cn. This is butane nitrile. Butane nitrile. Okay. This is how we can write the reaction. Next we have alcoholic AgCN, that is silver cyanide. Okay. When alkyl halides has been treated with alcoholic AgCN, alkyl isocyanide will be formed. What will be the product? Alkyl isocyanide will be formed. Okay. So how to write the general reaction? I have Rx, that is nothing but a haloalkane, which has been treated with alcoholic silver nitrate, AgCN, which is upon heating. Again, the Cn combines with R to form a alkyl isocyanide, and again Ag combines with X to form a AgX. So you can write the R by taking with the CH3 or C2H5 or C3H7 also, okay, and X as chloro, bromo, iodo, etc. Okay, so first I have methyl bromide, which has been treated with silver cyanide. What does happen? Silver combines with the bromine to form a silver bromide. Again, this Cn combines with the CH3 to form methyl isocyanide. Similarly, it is ethyl isocyanide. I'll go with the one more reaction by taking CH3, CH2, CH2, Cl. This is propyl chloride, which has been treated with silver cyanide. Silver combines with the cyanide to form, silver combines with the Cl to form a AgCl, and remaining the product will be CH3, CH2, CH2, Cl. Okay, this is propyl isocyanide. Propyl isocyanide. Okay, this is how we can rewrite the reaction with the AgCl. Next we have with the silver salts of carboxylic acid. With the silver salts of carboxylic acid, how does this haloalkanes will react? We'll see once. Okay, when alkyl halides has been treated with silver salts of carboxylic acid, esters are formed. What does it form? It forms an ester. So general reactions will be goes like this. This is a general representation of haloalkane. This is a silver salts of what? Carboxylic acid. You can see that carboxylic group will be represented as RCOOH. Okay. If the H has been replaced with RCOO with the silver, we write it as silver salts of carboxylic acids. Okay. With the haloalkane, what does it forms? This R combines with this CO and to form a ester, and this silver combines with the X to form a AgX. Again, you can take R by replacing with the CH3 or with the C2H5, and X can be replaced with the chloro or bromo. Okay. So here I have silver acetate. Just I have replaced the R with CH3 and X with the iodine. Okay. Silver acetate, which has been treated with iodomethane. What does it forms? This CH3 goes and attacks to this carbon atom, thereby it forms a methyl acetate, and silver combines with iodine to form a silver iodide. Okay, we have one more reaction by taking ethyl silver ethanoate. Why it is silver ethanoate? We have replaced the H by using silver, so it is silver ethanoate, which has been treated with ethyl bromine or bromoethane, you can say. What does it forms? Again, this Br combines with Ag to form a AgBr, and this C2H5 groups will goes and attacks here to form a ethyl ethanoate. Ethyl ethanoate. All this are what? Esters. These are the esters. Okay. This is how when haloalkanes has been treated with the silver salts of carboxylic acid, it forms a esters. Remember, how does it react with the alcoholic KOH or alcoholic KCN or with aqueous KOH or with NaOH or with alcoholic AgCN? What will be the product? And that should be very, very important, because it is very important to understand those reactions for your competitive examination point of view. Next, we have some of the reagent. And how does this nucleophile goes and attacks? What will be the substitution product, and what is the class of main compound? We will understand by looking at this table. Okay. Suppose if my reagent is KOH or with the OH, the nucleophile in this NaOH or with the KOH is O minus. You can write it as OH minus also. So substitution product will be ROH. This is an alcohol. Okay. Similarly, if the water if you take, the nucleophile itself is a H2O, and the substituted product will be again alcohol. Suppose if my reagent is NaOR dash, so nucleophile will be R dash O minus, and the product will be ether. Coming into the sodium iodide, the iodine itself is a nucleophile, so it forms an alkyl iodide. It forms what? Alkyl iodide. If you take the ammonia, ammonia itself is a nucleophile and it forms RNH2 and it is nothing but a primary amine. Similarly, R-NH2 if you take, the nucleophile which is itself will be R-NH2, it forms what? RNH-R-, it is a secondary amine. R-R-NH, R-NH, so here it forms what? R-NR-R, it is a tertiary amine. If you take KCN as a reagent, so direct reaction if you take, so K will replace this to form RCN, which is a nitrile or cyanide you can say. Similarly, if you take AgCN, so Ag and Cn will be form a nucleophile. So it forms what? Isocyanide or isonitrile as a main product. If you take KNO2, so here the nucleophile will be between the oxygen nitrogen. So it forms what? RON double bond O, it is a alkyl nitrile. Similarly, if you take AgNO2, so it forms what? Ag with the oxygen and nitrogen double bond with the oxygen. So thereby it forms RNO2, which is nitroalkane. If you take R-COOAG, so the nucleophile is R-COO-, so COO minus, so it forms what? R-COOR, it is an ester. Coming into the lithium aluminium hydride, so here the hydrogen itself is a nucleophile, it forms what? RX, which is a hydrocarbon. Coming into the R-M plus, here R- itself is a nucleophile, so it forms what? R and R, which is nothing but a alkane. This is how, just by recalling with the nucleophile with the different kinds of reagent, we got a different main end product. So in the next class, we are going to deal more about the SN1 reaction mechanism and SN2 we are going to understand. Okay. So I conclude my session here. So what are all the things which I covered? The physical and chemical property, which is very, very important for your examination point of view. Have a look on it. We'll meet you with the next session. Till that, take care. Be safe. Thank you.